Yeah, as I was saying, I've been working in the industrial North Sea for 10 years. So I went off to the oil and gas platforms and worked on UPS systems, installing, repairing, maintaining, and just taking care of all of the UPSs on various different platforms in the North Sea. And then I moved over to the USA and stayed within the UPS industry, in the oil and gas industry. Worked in the Gulf Coast region for a third-party service company. And then I moved to Amatex Solid State Controls 3 years ago. Started off as the training manager, and now I am the senior technical manager. Okay. Questions can be asked using the chat bar at the side of the webinar. And I see a question here already. Will the slides be provided? The slides will not be provided, but what we are doing is we are recording this presentation. And at the end of the presentation, that gets saved to the cloud somewhere. And hopefully we can provide everybody who attends this meeting with a link to the presentation, the video of the presentation. So hopefully that will work out well for everyone. Okay. So the objectives of the webinar today, first of all, is to understand the major UPS topologies, understand the blocks of different UPS systems, discuss the advantages and disadvantages of the various topologies, and then discuss the power flow and general operation of each topology. Now, obviously, the webinar is only supposed to be an hour, and we're going to have a question and answer session at the end. I'm going to go through everybody's questions and answer them at the end of the presentation. The best laid plans always don't work out the way that you want. So if we do overrun a little bit, that's not a problem. But just bear in mind, I've tried to cram in as much information as I can in a very short period of time. This is not going to make you an expert in UPS designs whatsoever. Hopefully it's just a good conversation starter, and what we're going to do is we're going to be doing this webinar hopefully once a month, and what we would love to see is people letting us know what you would like us to discuss specifically at some of our upcoming webinars. So remember, this is just a very broad outline of UPS systems in the industrial market. Okay. Questionnaire, how long will the presentation take? It's going to be roughly about an hour. Okay. Depending how much I talk. So the components that make up an AC UPS. So first of all, we have the normal source AC input, which can also be called the primary supply. And that's a problem with a lot of specific electronic equipment or electrical equipment. Sometimes there's a lot of different names for the same thing. So this is the input to the battery charger rectifier, the primary supply. Okay. And then the battery charger rectifier converts the normal source supply AC into DC. And that charges the batteries within the system and also supplies power to the inverter. And then obviously we have the batteries, and the batteries are there solely to provide backup power during a loss of normal source. Okay. And then the inverter converts that DC back to AC and provides power to your critical load circuits. Then we have a bypass source, which is the auxiliary power source, which once again confusingly can also be called the reserve supply. It's just a backup power supply, just in case everything fails, we have something to transfer to if absolutely necessary. Sorry about that phone. There's another phone in the office that I didn't realize. I'm going to have to disconnect that next time we do a webinar. Then we have a static transfer switch. Don't get this mixed up with an automatic transfer switch like you have on generators. This is an automatic switch that connects the load to inverter or the load to bypass. And it is a switch that has no moving parts in it. There's absolutely no moving parts in a static switch, hence the name static switch. It uses SCRs, which are silicon controlled rectifiers, to do the switching. So there's no arcing, and the switch switches instantaneously. Obviously, with a mechanical switch, there is a time delay from when the contacts open to when the contacts close and vice versa. And then we have a remote bypass switch or a bypass switch. That is a make before break switch. Usually, now there is caveats to that, but we're not going to discuss that today. But it's a make before break switch that removes power from the UPS cabinet, usually to allow safe maintenance procedures. And this is a physical switch or breaker arrangement. Okay. So on Amatec SCI UPSs, it is nearly always a rotary switch that has 3 positions, and they are normal, bypass to load, and isolated bypass position, but they can be a physical breaker arrangement as well. Some other UPS manufacturers use breaker arrangements instead of a rotary switch. Okay, so hopefully you're looking at this slide thinking, oh goodness me, this isn't going to be death by PowerPoint, is it? And just a load of slides with writing on it. No, that is not the case. From now on in, it's pretty much just graphics on the screen, and I'm going to have to make stuff up as I go along. So this is the a normal commercial style UPS. Now, Amatec solid state controls don't make commercial UPSs. We make industrial UPSs. And I'm not trying to sell you on anything today. I'm just explaining the different technologies and the different topologies. So with a commercial UPS, this one-line diagram that you see on the screen here, this is taken directly from one of our competitors. I'm not going to say which one it is, but it's a very good example of how a commercial or semi-industrial UPS works. Now, the first thing that you will notice is for all of the AC inputs into this UPS, they are all 480 volts 3-phase. So the AC input to the rectifier is 480 volts. The AC input to the bypass supply is 480 volts. And the output of the system is 480 volts 3-phase. So if that's not what your load circuits require, near enough, in every circumstance with a commercial UPS, you're going to have to buy an external transformer to transform the voltages from 480 down to what you require, whether it's 208, 120, whatever it is. Okay. And you can see on the bottom there that for a commercial style UPS, that the battery is near enough always 240 cells of lead acid cells. They are 2 volts nominal. So the nominal voltage for a commercial UPS battery is usually 480 volts. Now, if any of you are interested in the NFPA guidelines for arc flash PPE, that pretty much takes you into arc flash category 3 PPE to work on this battery here. So bear that in mind when you are designing a UPS, that the bus voltage of the battery can affect how maintenance is performed in the field. And the other thing is, in a commercial UPS, the DC bus between the converter charger and the inverter can be as high as 650 volts DC. And basically what the commercial manufacturers are trying to do is the higher the voltage, the lower the current inside the system. It's an inversely proportional ratio. So the higher the voltage, the less current that flows. So therefore the IGBTs, the cabling, everything inside the UPS can be smaller and therefore more cost efficient and more space efficient. So they're trying to save cost and save space by raising the voltages of the system so less current goes through it. And the other thing about a commercial UPS you can see here is there is no input transformer and no output transformer. If I go to this side here, there's no isolation transformers on this UPS, and we'll discuss that a little bit later on. The other thing about the commercial UPS is they have contactor arrangements in most cases, because they don't have that transformer, just in case there is a failure with inside the UPS. They don't want the DC to be able to propagate back onto the AC supplies. So they have control circuits that open contactors, CB1 in this circumstance and 52C, if there is a problem within the UPS itself, to stop the DC from the battery getting back onto the AC input or the output circuits. Okay. problem with contactors. If anybody has any experience in electrical maintenance, contactors are electrical mechanical devices with electromagnets in them, and they fail because there's moving parts and there's coils, and the coil can burn out. So contactors are not the most reliable things to have in direct line with the output of a UPS. Not my favorite mechanism of disconnecting between supplies, but that's what most commercial UPS manufacturers do. And as I said, they have no isolation transformers on the input or on the output in most cases. Okay. So here is the normal power flow within a commercial UPS. You can see in the bottom right hand corner of the screen, there is a red arrow that is saying where the power is flowing, and there's a green arrow that is saying that the power is energized and ready, but it is not supplying power at this time. Okay, so if you look at the diagram, you have the AC input on the left hand side, and that is where your 480 volts three-phase usually comes in. And it comes in from this point here through an external circuit breaker and into the UPS through contactor CB1. And then that AC then goes into the converter charger. And in this circumstance here, that will, it could be just a straight diode bridge rectifier that converts the 480 volts to a 650 volt DC supply onto the DC bus here. But the interesting thing about a commercial UPS is they also have a DC to DC converter. That's this part here, and what that does is that steps down the higher DC voltage here to a voltage suitable to charge this battery here. Okay, and for a 480 volt nominal battery, that actually gets charged at about 540 volts DC. Okay, so we're just trickle charging the battery. It's a very, very small amount of current that's going to this battery to keep it charged. Most of the power is flowing directly from the charger into the inverter. So the DC goes into the inverter, and the inverter converts that into AC. And in most circumstances in a commercial UPS, they're going to use pulse width modulation, PWM, to convert the DC back into AC. Then there is going to be some filtering, usually some capacitors and chokes or inductors on the output of the system to turn that pulse width modulated waveform into a sinusoidal waveform. And then that AC goes through this contactor here and directly out to your load circuits. And you can see at the top of this diagram, we have the bypass supply coming in here. It is energized. CB3 is closed, so the power goes to the static transfer switch, the static switch, and is ready to be switched if something goes wrong in the system or you want to do maintenance on it. And also power is going to this contactor here, which we'll explain in just a moment. Okay, so this is normal operation. This is how the UPS should be working in normal operation. So what happens if we have an AC input failure? And that is why the UPS is there. Basically, we are trying to protect against a fluctuation or output of the AC input to the system, and then protect the loads from that disturbance. So what happens is, you can see on the left-hand side, the AC input has gone out. So the battery starts supplying power through the DC to DC converter into the inverter. And in truth, there is no switching involved here. A lot of people says, oh, it's switched to battery. And that's not the case. It doesn't switch to battery. The charger and the battery are connected in parallel. So if the charger disappears, the DC from the battery is just there. It's just like unplugging the power from your laptop. There's no switching goes on inside your laptop. The battery just takes over immediately. And that's exactly what happens in a UPS as well. And the inverter doesn't see any of this. All it cares about is that it has DC available at the input to the inverter. So it converts it into AC. Okay. But as you can see, we don't switch to bypass. The bypass supply is still present, But what we want to do is we want to switch to battery and keep the power that is going to this output a pure sine wave without any interruption whatsoever. Okay. Now, once we've been on the battery for a considerable amount of time, whatever the design life of that battery has been designed for, then there has to be some form of circuit that says, okay, my battery is now depleted. I need to disconnect from the battery so I can prevent over discharging it. And we'll discuss that later as well. So inside a commercial UPS, it could be that the inverter just switches off, it trips the battery breaker, something disconnects the connection between the battery itself and the inverter. And what happens in that circumstance is there will be a circuit that says, okay, I'm just about to do this. Let's transfer to the bypass supply. And what happens is the static transfer switch, you can see on the screen here, this static transfer switch says, okay, I'm synchronized. The inverter is always synchronized with the bypass supply. And what happens is it says, okay, my battery's discharged. I'm going to switch off my inverter. Let's transfer over to the bypass supply. And it sends a signal to the static transfer switch, and this switch is on. So as you can see, the power now flows from the bypass through the static switch and out to the output circuit here. Okay, that is now the power flow. And in a commercial UPS, the static transfer switch in most cases is not rated to carry the load all of the time. It's just an instantaneous transfer. The static transfer switch allows an instantaneous transfer, and then what happens as soon as that transfer has occurred in a commercial UPS, then the contactor 52S will then close and basically bypass the static transfer switch, and the power flow will now be directly from your bypass supply all the way through 52S, this contactor here, and directly out to your output. Okay, and that's the same if the inverter had failed as well. The static transfer would instantaneously transfer, and then this contactor here would take over. Okay. There is a question that's just come in. Does this drawing show that the bypass is always connected to the output through the normally closed contactor 52S? Unfortunately, the way that the manufacturer draws this, it's not showing you the actual condition of these contactors in normal operation. And to answer that question, the contactor 52S would normally be open when the system is running in its normal state. So yes, it is a bit confusing. I do apologize for that. It should be normally open, but I don't have the ability to edit the competitor's UPS drawing, so I do apologize for that. Okay, so now we will move on to an Amatec SCI double conversion industrial UPS. Okay. And the first thing that you will notice now, this is pretty much the most common UPS that we sell. So we are a custom UPS manufacturer, so we can design a UPS to give you whatever you want. You can have different size batteries, different AC outputs, different AC inputs, whatever you want, we can give you. But this diagram here is pretty much the most popular UPS that we sell, and that is we have a 480 volt three-phase AC input. Oh, sorry, I didn't mean to progress the screen. Let's see if I can go back. There we are there. Oops, done it again. My apologies. That's better. Okay, so we have a 480 volt AC input here, three-phase. That goes into our system. We have our AC input breaker on the front of our UPS, and then we have an isolation transformer, and I'll explain the importance to that in just a moment. Okay, our bypass source has to match the AC output because remember they're synchronized together. So our most common UPS design has a single phase 120 volt AC output. Okay, So therefore our bypass supply has to match that. So in this circumstance, the bypass source AC input is 120 volts AC. Okay, and our most common battery is a 60 cell lead acid battery, which has a nominal voltage of 120 volts DC. Okay, you can see that we have two static switches in our UPS. The commercial UPS only had one static switch on the bypass supply. This is a far more robust design and gives us isolation when we choose either one of the static switches. Okay, and the static switches are purposely designed to carry the load at all times. I'll show you that in just a moment. The importance of the isolation transformers has to be stated. We always have to prepare for faults inside a system. Now remember, we have DC here from a battery, so we have to think about what happens if something inside this rectifier charger fails, okay, and allows a direct connection between the DC bus within the UPS to the AC input that comes in here. And if anybody knows anything about transformers, you will know that a transformer does not pass DC. It's impossible for DC to get through a transformer from the secondary to the primary or from the primary to the secondary. So if something inside this battery charger or rectifier fails, that DC cannot propagate back onto your AC input circuits. Now remember, this AC input is being fed by an MCC within the plant somewhere. So you don't want DC getting back onto there, because that could cause misoperation of many other AC circuits connected to that MCC, the motor control center. That would be a very bad day if DC got back onto there. You could have transformers saturating, you could have coils operating in a way that you wouldn't expect. It's a very bad thing. So with the installation of the isolation transformer here, there is no way that the DC from this battery can get back onto the AC input. And that is also true for the inverter. If something in the inverter fails, there is no way this DC can get through this transformer and get onto the load circuits. It's impossible. So that is the biggest difference between an industrial UPS and a commercial UPS, because most commercial UPSs are transformerless. And there's a reason those transformers are there, and it's very important. Yes, it does increase the size of the UPS, it does increase the weight of the UPS, and it does increase the cost of the UPS inherently. But there's a very good reason for why they are there. Okay. So once again, here's the normal power flow for an industrial UPS, and it's very similar to the commercial UPS. The AC input comes in on the left, goes through a battery charger rectifier. The output of that rectifier is connected directly to the batteries. There is no DC to DC converter in between there. Okay, so we are charging a 60 cell battery at 135 volts DC. That DC goes into the inverter. The inverter converts the DC back into AC. Now we have two designs of UPSs. You can get a ferroresonant UPS, which uses older technology but more robust technology, or we offer our PWM DPP UPS, which is similar to the commercial UPSs. But both of them create a near perfect sine wave on the output. That goes through a transformer, which then goes through the static switch. So you can see this static switch is in circuit all of the time. Power flows through the static switch, out through the manual bypass switch, which is in the normal position, out to the AC output circuits. Okay, so that is a normal operation for an industrial UPS. Once again, if the AC input fails, we don't transfer to battery, we don't switch to battery. The battery is just there, and it just takes over the power to the inverter, and the inverter doesn't see anything happen. Okay, it just sees I've still got DC, so I'm going to carry on turning that DC into AC, and that flows as normal out to your AC critical load circuits. And then in our systems, we have a circuit within the UPS that Once the battery gets down to 1.75 volts per cell, which is 105 volts DC for a 60 cell system, we have a circuit in the UPS that says, okay, we have to disconnect the batteries to protect them from being over discharged, because that's the worst thing that you can do to a battery, is discharge it too deeply and leave it discharged for a long period of time. It causes sulfation on the plates of the battery and seriously reduces the life of the battery. So we want to protect against that. So our system actually trips a DC input breaker on the UPS, and just before it does that, it sends a signal to the bypass source static switch. It says, okay, you're in synchronization with the inverter, transfer to the bypass supply and transfer the loads to bypass, and then it trips the breaker and the inverter shuts down. Okay. And then in our systems, whether you buy a remote manual bypass switch or a standalone system that has a bypass switch on the front of the UPS, you will be able to go into maintenance bypass, which supplies power from the bypass and bypasses the static switch entirely through the bypass switch and allows you to do maintenance within the UPS system without there being any power inside there. Okay, so we've discussed single UPS systems. So now what we want to discuss is the different arrangements where you want redundancy. You want backup to your backup, because obviously the loads that we are supplying in petrochemical industry are critically important, not only for production, but for safety also. So one of the most common designs that you can get is a dual parallel redundant UPS, okay? And that's when you connect the output of two UPSs in parallel. As you can see here, the output of these two static switches are connected in parallel. Now for ease, I haven't shown that there's usually a AC distribution panel between the output of the UPS and the load circuits. In truth, that's usually where the parallel connection is made. The thing about a redundant UPS is there has to be some control circuitry, and it's very complex control circuitry that not only makes the inverter synchronize with the bypass supply, but what we have to be able to do is make sure that both inverters can be parallel together. They have to be in sync with each other, okay? And that takes complex logic, because you've got to understand that there is power factor involved, there's leading and lagging issues. So we have to take care of all of those issues to prevent circulating current between these two UPS systems. So it is very, very complex to connect two UPSs in parallel. And you cannot connect two different types of UPSs together. You can't connect two different manufacturers. You can't connect two different styles of UPS from the same manufacturer. They have to be identical UPSs, and they have to have the control circuitry designed in to allow them to run in parallel. So in normal operation, both UPSs have power flow as normal coming from the AC input through the rectifier. They keep their batteries trickle charged. The DC goes through the inverter, and they go out through their static switches to the load. So they're both running in parallel, sharing the load together. Okay. So the other important thing about a redundant UPS situation is if your load is designed for, let's say, 20 kVA, you think you're going to have 20 kVA of load and future-proofed, obviously, then what you have to do is you have to have two fully rated UPSs. This one has to be 20 kVA and the bottom one has to be 20 kVA. Okay, so it is more expensive because you have to buy two fully rated systems, but it does give you the redundancy that you need. So we'll move on to the next slide. Well, what happens if the primary AC supplies for one of those UPSs that are connected in parallel? We're not on an Amatec SEI UPS. It operates as a single UPS. Basically, this bottom UPS here will go onto battery, because remember, the inverter doesn't care where the DC comes from. So what will happen is the top UPS here will carry on going regardless. This bottom UPS will go on to battery operation. You'll get an alarm on this UPS to tell you you are in battery operation. But the outputs of both UPS systems will still be connected in parallel through the static switch, and the loads won't see any issue with this whatsoever. Okay. And once again, if the battery gets to a point where it has depleted too far, we have to do something about that. So we disconnect this battery automatically. The inverter will switch off. And what happens in our system is this system won't transfer to bypass because we're connected in parallel. Okay, connecting to a bypass supply in parallel with an inverter supply is a very bad thing. So what happens is when this inverter on the bottom UPS switches off, we actually turn off the bottom static switch here. It goes open, and what happens is we just allow the healthy UPS to supply the load circuits at this point here. Okay. Now, the other thing a lot of people ask is what happens if both inverters fail? Okay. It's a very rare possibility, but we have to be able to allow for that. So let's say this system fails and then the other system fails afterwards. What happens is we will transfer to bypass through the bypass static switch and through to the load circuits. So basically it's a really good system. You have to have 2 UPS failures to go over onto bypass supply, which is very, very rare indeed. Okay, so that's a parallel redundant UPS. Now there's another way that you can connect a dual redundant UPS, but without connecting them in parallel. Now obviously this drawing on the screen here is a little bit messy, so what I've done is the top UPS here, the power flow is drawn in red or pink, and the bottom UPS, the power flow is drawn in orange. And we'll call the top UPS UPS A and the bottom UPS UPS B. Okay, now in most systems, in a lot of systems should I say, the UPS is supplying the DCS for a control room, so the distributed control system for a control room. Okay, now modern technology knows that you're going to be using UPS systems to power their DCS, and what most DCS manufacturers do now is they allow you to have multiple AC inputs to their DCS system. I've seen dual, I've seen triple inputs to DCS systems. And what that allows us to do is remove the complex circuitry that allows the 2 UPSs to synchronize together. Okay, and basically what we're doing is we have 2 standalone UPSs. UPS A, if you follow the power flow, what it's doing is it is supplying the power to this top power supply, which is within the DCS system. Each DCS system converts the usually 120 volts AC back into a DC voltage that allows the DCS system to work. UPS B, the bottom UPS, also has a supply going into the same DCS panel. And then the outputs of the DC within the DCS system then keeps the DCS system operating. Okay, and you can have as many DCS panels as you want as long as you stay within the rating of the UPS. Okay, so I know this is a little bit confusing, but these UPSs are not connected in parallel. So in this circumstance here, if you really wanted to, I don't know why you would, you could have one UPS manufacturer connected as UPS A, and you could have a completely different UPS manufacturer as UPS B. Okay, that's not a problem because the outputs are not connected in parallel. Okay, so what happens if we have failures within a system where the loads are connected like this. So we'll talk about UPS-B again. Once again, the AC supply has disappeared. The inverter goes on to battery operation. Remember, the output doesn't see any of this. The load continues to be supplied, the top one here by UPS-A and the bottom one here by UPS-B. The loads are still powered up without any issues whatsoever. Now, if the battery on UPS-B completely discharges, then the system is going to transfer to its bypass supply. So you follow the bypass supply down, orange, through the bypass static switch of UPS-B. So you're going to have the top power supply in the DCS system supplied by UPS-A inverter, and the bottom power supply powered by UPS-B on bypass. Let me clarify that. I think I said that wrong. So the top power supply is fed from UPS-A inverter, and the bottom power supply is fed from UPS-B bypass. You can do that on this system because it's only the DC outputs that are connected in parallel. Hopefully that makes sense. So the next design that you can have is the cascade UPS. Now, what you have, let me explain this. Let's call this bottom UPS here UPS-A, and we will call this top UPS here UPS-B. UPS-A is the main UPS, and UPS-B is the backup UPS. You can call UPS-A the master and UPS-B the slave, if that's what you want to call it. But basically what it is UPS-B is actually the bypass supply for UPS-A. Okay, so once again, we get away from the complex logic circuitry that's required to have two UPSs in parallel. These UPSs are not in parallel, so you don't need that control logic. So once again, in this situation, you can have one type of UPS, one manufacturer of UPS as UPS-A, and you can have a completely different manufacturer of UPS as UPS-B, if that's really what you want it to do. They are interchangeable. There is no restrictions on that whatsoever, as long as both are still rated for the load. So obviously if UPS-A is a 20 kVA UPS, then UPS-B has to be a 20 kVA UPS as well. So normal operation, once again, AC into the rectifier, charge the batteries, power to the inverter, out through the static switch. Okay, so that's normal operation. Now, if we have the AC fails on UPS-A, the primary UPS, all that happens is we go to battery. Okay, remember, we don't switch to battery, we just go to battery. The inverter continues turning that DC into AC through the static switch. Your load circuits don't see any issues whatsoever. Okay, now obviously that battery is discharging, and at some point, if the power doesn't come back on, we are going to have to protect that battery from being over discharged. So if the battery depletes, then the system will transfer to bypass. Okay, so UPS-A has transferred to bypass, and it does that through the bypass static switch. So this is the static switch for UPS-A, and what happens is that allows power from UPS-B now to feed through its own static switch. So this is the static switch within UPS-B. That flows into the static switch for the bypass on UPS-A and into the load circuits. So we still have clean, filtered, pure AC going into our load circuits. Okay. Let me see, I've just got a question here. I'm used to a single battery for both UPSs. This is a UPS in parallel, not cascade. To clarify, when one UPS goes down and is on battery, will that UPS act as a load on the other UPS? I might have to answer that question at the end. I'm trying to get through as much as I can, and I'll save that one for the end. We'll go back to this slide, hopefully, and we can discuss that. Okay, I'm not ignoring the questions. I just want to save them for the end if possible. Okay, so hopefully that explains cascade. And obviously, if something inside UPS B, the slave UPS, fails, then we still have the actual bypass supply to transfer to when that happens. So once again, it's a really robust system. This is actually my favorite design of system because it allows easy maintenance. There's no complex control circuitry between the two UPSs that you have to run additional cables for. I just really like this. It's a very robust way to connect two UPSs together to give redundancy. A lot of people complain in this situation that UPS-B, the slave UPS, is never going to be supplying load and therefore you can't rely on it. I believe that then therefore if you do the correct maintenance once a year, you are going to switch to the slave UPS while maintenance is being performed. And with the technology we have these days, whether the system is loaded or not, they are very, very reliable. But that's just my opinion. Everybody else has their opinion. Okay, so the next thing I wanted to discuss is bypass switches. So once again, this is a diagram from one of our Amatec SEI UPSs, and you can see the bypass switch. The contacts are here, the top left, and they're also here. There's a little bit messy with the arrows, but that is the contacts here. Okay, and the key, we have normal, which is a normal position. Obviously, we have three positions: bypass to load, which is the middle position, and bypass isolate. Okay, so it's usually three positions on our bypass switches. It could be two, but we do recommend three. Okay, so in normal operation, the UPS feeds power through its inverter, through the static switch, and then through the bypass switch in normal position. So it goes through this contact here up to the load circuits here. Okay. Now, if we move the bypass switch to bypass to load position, this is the power flow. Now, I want to caveat this. You have to follow the operations procedure on the front of your UPS to do this. And in truth, you always have to transfer the static switch to bypass before you transfer the manual bypass switch to bypass. I've just got a comment there saying the video has froze, so hopefully that is just one user that the video has frozen for and not everybody else. I have no way to check it, unfortunately, so I'm going to carry on going regardless. So in the bypass to load position, power now flows from the bypass around the static switch and out through this bypass to load contact here to the load circuits. And the important thing to remember about the bypass to load position is it actually still keeps the bypass static switch inside the UPS energized. And really, the only reason we have the bypass to load position is for service engineers to come, do work on your UPS, and then test the operation of the static switch within the UPS while you are still on bypass supply. It allows us to do some testing of the system. Okay. So hopefully that explains that. And there's a very small nuance when we go from bypass to load to bypass isolate. It's just a very small difference, and you'll see it on the output here, and you'll see this contact here change. So I'll move to the next slide. And the bypass isolate position, what it does is it actually isolates the bypass supply from the static switch inside the UPS, and it also moves contact from this bypass to load position to this bypass isolate position. So if you imagine, and people say, well, why would you want to do that? Well, the really good thing, especially about a remote manual bypass switch that is external to a UPS, if you have this primary AC supply isolated, you have the battery isolated, and you have the system in bypass isolate position. So these are actually the output terminals from the UPS here and the output terminals from the UPS here. What you can do is if you have the system in bypass isolate and you have performed a full lockout tag out on the system, you can actually remove the UPS from the system and replace it with another UPS while the loads are still energized. So it allows you to do work, very intrusive work on a UPS, including complete replacement, while you still have the bypass supply supplying the load. Good morning, everybody, and welcome to the Amatec Solid State Controls Understanding UPS Designs webinar today. What I'm going to do is give everybody a little bit of time to log in, get situated. So I'll probably get started in just a few minutes. My name is Craig Williams. I'm the UPS Technical Manager here at Amatec Solid State Controls. I'm just trying to get the presentation to move on. Okay, there we are there. So I'm the Senior Technical Manager at Amatec Solid State Controls. I've got 20 years in the industrial UPS industry. Basically, I started off in the North Sea oil and gas industry. Okay, so now we're going to move on to the common misconceptions that we hear about UPS systems. And the first one is, I need a three-phase 208 volt output on my UPS. And this is a very common misconception because in most cases, there is never a 208 volt load connected to the UPS system. It's usually always that the 208 would then go to an AC panel, the neutral is run to that panel, and all of the loads that come off that AC distribution panel is 120 volts line to neutral. Okay, it's very, very rare that there is a 208 volt load supplied by a UPS. And the thing about having 208 volts coming out of the UPS is they will not clear a fault on the output as good as a single phase UPS. And many people say, well, how can that be? Well, remember, if you've got a 10 kVA three-phase UPS, then each phase on the output is only rated for a third of the current for the total system. So each phase can only supply 28 amps, okay? But a 10 kVA single phase UPS, you can get 83 amps out of the system. So obviously that's 3 times as much current. And if you look at this trip curve, just a general trip curve for a breaker, you can see that if you install, let's say, a 10 amp breaker inside, on the AC panel of your system going to a load, well, obviously you need 3 times the amount of current to get into that B region on this trip curve, which will cause a trip quicker than 2.53 seconds. So on a single phase UPS, if you put a 10 amp breaker on the output, it's going to take it up to 2 to 3 seconds to trip that breaker. So that's 2 to 3 seconds that a fault can cause a dip on the output of the system before that fault is cleared, and in truth the system will transfer to bypass. But it's not, if you don't have a bypass supply, say the power has gone off and you're running on battery, then that's really bad. That can cause the whole loads on the system to see an undervoltage situation, and it could cause them to trip off. So it's not a good situation. And as you can see from this time curve, for a 10 amp breaker, a single phase UPS will give you 8 times the amount of current. So that would be, if you look at this time curve here, that means it's going to trip the breaker within 10 milliseconds. Okay, so that's quick enough. I think that's half a cycle, maybe a full cycle. That's quick enough to it not affect load circuits. Okay, so that's why it's very important when you are designing a UPS. You know, if the existing UPS that you have there is an old commercial UPS and it uses a 208 volt output, consider changing the AC panel to a single phase. Consider changing the UPS to a single phase, because you will find that all of the loads that UPS supplies are single phase. Okay, so that's the first common misconception. It is much better to have a single phase UPS connected to your 120 loads, without a doubt. The second one is a 10 kVA UPS will give you 10 kilowatts of power. Now, that is not true. Most UPS systems are rated at 0.8 power factor. Amatec SCI does offer UPSs that are designed at Unity power factor, but we're a custom UPS builder, so we can do that, and basically we just overrate the system. You've got to understand that most of the loads that are connected to a UPS have capacitive, inductive loads, and it's mostly power supplies that our UPSs are connected to, and that brings down the power factor to usually less than 0.8. So therefore, if you have a 10 kVA UPS, it's only going to give you 8 kilowatts of real power. So if you connected a purely resistive load bank to a 10 kVA UPS, you can only crank that UPS up to 8 kilowatts before the UPS will start to go into a current limit situation, okay? And that's because the power factor is unity for that purely resistive load. So you're not going to get 10 kilowatts out of a 10 kVA UPS rated for a 0.8 power factor. And like I said, remember, most of the loads connected to a UPS system include power supplies and other inductive capacitive loads, and it tends to always decrease the power factor down to 0.8, if not less than that for older power supplies as well. So that's another misconception that a lot of people get wrong. The next misconception: we lost power to the input of the UPS. Why didn't we switch to bypass? And actually, that's a very good question, because a lot of people say, well, we want to protect our batteries, and if the bypass supply is available, why don't we switch to bypass before we go on to battery operation? So remember, the AC input to the UPS is nearly always fed by the same main HV bus upstream of the MCC, okay? So if the MCC that feeds the AC input to the UPS has tripped, then that usually means that MCC is seeing a lot of other things, a lot of disruption. It's in an unstable situation. And that may mean that the MCC that feeds a bypass is seeing also a large unstable situation, pumps stopping and starting that can cause voltage dips on the bypass. So if we transfer to bypass, these dips could cause the load circuits to operate erratically. And you can see in this picture here, you've got your UPS at the bottom, and as you can see, the UPS primary AC input is fed from MCC1, okay? And what's happened is let's say there's been an input transformer fault on MCC1. So MCC1, all of the breaker distribution inside that MCC has failed. So therefore, the primary AC input to the rectifier has failed. Now, obviously, the transformer that feeds MCC2 from the 4160 supply, it's still okay. So it is still supplying the bypass to the UPS if necessary, okay? But remember, there could be other MCCs fed off that 4160 supply, and there can be some huge pumps on, let's say, for example, on this MCC3, you can see that there's a 3-phase motor connected there, and it could be a 4160 motor, it could be a 480 volt motor, but it's a really high powered HP motor. And when those motors start and stop, they cause a huge amount of disruption on the bus that feeds that supply. So as you can see, the bypass may be seeing dips and peaks, and actually frequency changes as well as these pumps stop and start. So if we transferred to bypass supply when we lost the primary AC input on this situation, that would be a bad thing, because if we went to that bypass supply, the loads would see that poor waveform. So it wouldn't be a good situation. But if we stay on battery and we stay on inverter, because it's a synthesized sine wave, the output to the load circuits will be completely and utterly pure. There will be no disruption on it whatsoever, no matter what's going on in the plant. So that is why we never transfer to bypass if we lose the AC input to the rectifier. We always go on battery because the UPS is designed to always keep that synthetic pure sine wave going out to the load circuits, because that's the sine wave we can trust at all times. So hopefully that explained that one. The next misconception is the battery breaker on the UPS tripped. Do I have a bad battery? Well, battery manufacturers specify the rating of their batteries to a specific end voltage. So I'm going to use an Enesys 3CC9 battery as an example. And it says on their datasheet that it will give 200 ampere hours at the C8 rating to 1.75 volts per cell. And what that actually means is that the battery will give you 200 amps total for an 8-hour period. And there at the end of that 8-hour period, the voltage of each cell should be 1.75 volts per cell. And if you calculate that out, what it's saying is it will give you 25 amps per hour for 8 hours. Okay, so battery manufacturers recommend that a lead acid cell should never ever be discharged past 1.6 volts per cell, as it can lead to damage that cannot be reversed. Basically, it causes oversulfation of the plates, and it can be a really bad situation, especially if it is left in the discharge state for a long period of time. But all battery manufacturers recommend do not discharge a battery past 1.6 volts per cell. So the only way to protect the battery from an over discharge is for the UPS to prevent the battery going below this voltage. So in an Amatec SEI UPS, we have a function that is set that the battery input breaker will trip at 1.75 volts, which is a manufacturer's recommendation, times the number of cells. So that's 60 times 1.75, which is 105 volts DC. So once we get to 105 volts DC, the system will trip the DC input breaker, and that means the battery cannot be discharged past that point. Okay. The next question that a lot of people get wrong is we had a fault on a load circuit and the UPS transferred to bypass. Why did it do that? So you have to remember that inverters have devices inside them that have to be protected from overcurrent situations, and that's usually the IGBTs in the inverter bridge. IGBT is an insulated gate bipolar transistor. Okay, now when you buy these transistors, you have to buy them whether they're going to supply 100 amps, 200 amps, 50 amps. You buy them specifically for a specific amperage. So think about it this way. For a 10 kVA UPS, the output current, as we've discussed before, is rated at 83 amps at 0.8 power factor. So at a certain point after the 83 amps is reached, the system has to go into current limit to protect those IGBTs, okay? Because the IGBTs that have been installed in that UPS will be rated for some value above 83 amps. And in truth, in an Amatec SEI UPS, we oversize everything inside our UPS because it's a rugged industrial system. So in truth, it's probably 200 amp IGBTs that are in this system, but we still have to protect them. So to protect them, we have to put the system into current limit. It's an electronically controlled circuit, and it simply reduces the output voltage of the system to maintain the current at a certain level. Well, a lot of people say, well, why reduce the voltage? Why can't you just reduce the current? Well, here's the example. You have to think of the load as a resistance, okay? So for a 10 kVA system, if the current is 83 amps, that means the load is 1.44 ohms. And you work that out using Ohm's law. Resistance is equal to voltage divided by current, which is equal to the output of the UPS will be 120 volts. And we're saying that the current is 83 amps. So that means the overall resistance of all the loads connected in parallel is 1.44 ohms when we are supplying 83 amps. But let's say the load increases. Somebody adds more load to the system to cause it to go above the 83 amps. And the only way that happens is if the resistance decreases. If you add load to a system, the resistance of the load in total is going to go down. So let's say it goes down to 1 ohm. Then we have to use Ohm's law, I is equal to V over R, which is equal 120 divided by 1, which means we will be supplying 120 amps if the load has been changed to 1 ohm. And that's too high. Obviously, it's above the rating of the 10 kVA UPS. So the only way to reduce the current electronically, now think about this, we can't change the load. Okay, the load is the load. You can't change anything in the load. So you can't change the resistance in the load unless somebody goes out and actually physically switches something off on the load circuits. But that needs manual interaction. So the 1 ohm of resistance is not going to change. Okay, so the only other thing that we can change to lower the current is the voltage of the UPS output. Okay, so what's going to happen is the UPS is going to say, okay, my output has to be no more than 83 amps. What can I do to make my output 83 amps again when I've actually got 120 amps being demanded? So the only way to do it is it says, okay, I'm going to reduce my voltage. And using Ohm's law, once again, what's going to happen is the UPS is going to say, right, I need to get 83 amps again. So the voltage is equal to the current times the resistance. And we know that the resistance is 1 ohm. So, and we know we want the current to go back to 83 amps. So the output of the inverter is going to be reduced to 83 volts. Okay, that way we limit the current to 83 amps. And that's too low for many loads connected to the system. And we have a low voltage trip setting on the static switch of the system that is monitoring the output of the system. And it says, okay, my output has gone down to 83 volts. That is too low a voltage. I'm going to have to transfer to bypass. Okay, and that is why the system transfers to bypass if you have a fault on the load circuit. And what happens is, to be honest, the bypass supply is a much more robust source. So if there is a medium to high resistance fault on the output of the system, the UPS may not clear it, but if you transfer to bypass, there's a huge amount of power behind that bypass supply because it's just coming direct from the MCC, and it will clear the fault much quicker than the inverter. But that is why if there is a fault on the output of the system, it will usually always transfer to bypass because the inverter goes into current limit to protect the IGBTs from being destroyed internally to the UPS. Hopefully that explained that one. Okay, and there's a picture to show what happens. So if there is a fault on the load circuit, then the current through the inverter from the DC to the AC is going to be too high. So the system recognizes that it lowers the voltage on the inverter to keep the current below 83 amps, and in doing that the voltage will dip too low and the system will transfer to static bypass. Okay, another common misconception, everybody says this, all the PCBs should be plug and play. We should be able to supply you any board and anybody should be able to install it. That would be fantastic, but unfortunately all PCBs have analog to digital converters on them, and we need to use resistors to drop the sensing of the outside world, the analog values, into the analog to digital converter, so we convert that analog signal into a digital signal, and then the UPS will decide what to do with all of those inputs. Now, the issue that we have is all resistors have tolerances. When you go to a resistor manufacturer, they will say, okay, this resistor that you're buying has a 1% tolerance. And what that means is if it's a 10 ohm resistor, that will be 0.1 ohms high or 0.1 ohms low. It's not going to be guaranteed to be 1 ohm. And if it's a 5% tolerance, it's going to be half an ohm. The value that it can change goes up. So we don't know what the value of that resistor is going to be when we install it in the system. So this means that the PCB, the printed circuit board, has to be calibrated to the system that it is going to be installed in. So if a board is replaced, that board will also need to be calibrated. You have to calibrate every new board in a system. And near enough every UPS manufacturer, every OEM, the calibration function is protected in the menu system. And that is to prevent a situation that could cause the UPS to fail or be damaged if somebody goes in, doesn't know what they're doing, and miscalibrates the system. It can cause a huge amount of problems. For example, if somebody accidentally calibrated the system to make it think that 100 amps going through the output is actually 10 amps. Okay, now that's going to affect the current limits of the system. It's going to think that a 100 amps actual current flowing is 10 amps, and therefore the current limit isn't going to go into operation. So therefore it's only going to start to go into current limit when it thinks it has 100 amps, which will in truth would be 1000 amps, and everything is going to be blown to bits inside the UPS. So it is very important that we password protect the calibration menu in the system to prevent those things from happening. And on top of that, we also have continuing R&D software development and obsolescence. We have parts that are going obsolete so quickly in this day and age, processors and many other chips and ICs, they're going obsolete all the time, and we have to stay on top of that. And that means we have numerous software revisions for many similar PCBs. So once again, we're in a situation where if we're replacing an old board with a new board, the new board may have a software revision on it, and things need to be changed when we install it. And those changes have to be done by a certified field service engineer who can come and update the system to accept that new board. So yes, in an ideal world, it would be fantastic if the PCBs would be plug and play. But unfortunately, we just can't do that. It's not possible. So in near enough every situation, you're going to need a field service guy to come out and recalibrate the board when it's put inside a system. Okay, hopefully that explained that one. The next misconception: I can move the manual bypass switch to bypass without following a procedure. You can, but you may have a bad day if you do that. Because remember, the bypass switch is a make before break switch. Well, it should be a make before break switch. And this intentionally parallels the outputs of the UPS to the bypass supply for a very short duration of time while the switch is moving from normal to bypass to low position. So if the output from the UPS is on inverter, there can be situations where the output and the bypass will not be in sync. Okay. And an example of that is, let's say the UPS thinks the bypass is out of tolerance. Maybe the bypass voltage is low or the bypass frequency is out of tolerance. Then what happens is the UPS says, okay, my bypass is not healthy enough for me to synchronize to, so I'm going to run at my own frequency and ignore the bypass until it comes back into tolerance. And at that point there, you can have two unsynchronized supplies. Okay, and obviously on the UPS it will tell you that it's not in sync. Well, it should tell you it's not in sync. And then there's going to be a phase difference between those two voltages, And if you move that switch, you parallel two supplies that are out of phase. That can lead to UPS damage and can even trip the incoming bypass breaker because of high circulating current. This picture here shows you better what happens. So let's say, for example, the inverter output is not synchronized to the bypass supply. So as you can see on the bottom waveform, when you are about to move that bypass switch, let's say you are at the bottom of the sine wave for the inverter output. But because you're exactly, let's say for this example, you're exactly 180 degrees out of phase, the bypass supply is going to be at the top. It's 170 volt peak. So in truth, if you follow where that contact is, it's going to change. The contact is where it says difference of 340 volts. If you measured across that contact at that exact time with a fluke, you are going to measure a 340 volt peak to peak voltage difference. Okay, I can't remember what the RMS value for that is. I'm sure somebody clever out there can work it out. It's going to be around about 240 or 50 volts. I can't remember, but there's going to be a huge voltage difference. And the only thing that's going to dictate where the current flows there is the resistance of the cables, the contacts, and everything else. So if you move the bypass switch when you have an out of phase supply, that is going to cause, in most cases, the bypass to feed current back into the inverter bridge. And that's going to cause usually damage to the inverter bridge. And that high current, if you think about it, that high current is probably going to cause the bypass source to trip upstream at the MCC because there's uncontrolled high current. And if you've moved that switch from normal to bypass, then that means the switch is in bypass position now. And if the bypass breaker upstream at the MCC trips, then that means you've lost power to your load circuits. So always follow the procedure on the front of your UPS when you're transferring from normal to bypass. Because what near enough every UPS manufacturer will tell you to do, the first thing that you have to do before you move the manual bypass switch is to transfer the system to static bypass by pressing the button on the front of the system. And what that does is the output of the UPS then will be exactly the same at the bypass. So the voltage difference across that contact will always be exactly the same. It will be a 0 volt difference across that contact, and therefore you can move to bypass safely. Okay. The next question is, I have a parallel UPS. When I switch to bypass on UPS A, it shows that the static switch is open on UPS A. Why didn't UPS A switch to bypass? So as discussed before, it is never good to have two voltage sources paralleled if you cannot control all aspects of both sources. So when you have a parallel system, remember, both inverters are looking at each other and they're perfectly synchronized together. And they're looking at the power factor, they're looking at active power, reactive power, and all that good stuff. So they're completely in control of each other and they share the load perfectly. But if you press the button to transfer the UPS to bypass, the system is intelligent enough to know that that's not a good idea, because if it did go to bypass, you would have a situation where the bypass could actually fluctuate. You have no control over the bypass supply. There may be big pumps being started. Something in the external world could be causing that bypass supply to fluctuate. And if that happens, the electronics in the inverter, there's a little bit of a delay in how they react to synchronizing with the bypass supply, and it's not going to react quick enough, and it could cause an out of phase situation. And when that happens, that could introduce high circulating current, just like we mentioned in the previous slide, and that can be very, very bad. So that is why when we have parallel systems, if you press the button to transfer one system to bypass, it says, oh, okay, I'm clever enough. Your other UPS is still okay. Instead of transferring to bypass, I am just going to switch the static switch off so UPS A is no longer connected to the load. UPS-B is connected to the load, UPS-A will just disconnect itself from the system. Okay, so you can see in this picture here, the bottom UPS is UPS-A, the top UPS is UPS-B. So we pressed the bypass to load button on UPS-A, and you can see the static switch on the output of the inverter. It's not energized anymore on UPS-A, but if you look at UPS-B and follow the red all the way through, the static switch for UPS-B is energized and is supplying the loads. Okay, so at this point here, the A UPS is not supplying any power to the loads anymore. That static switch is off. The next question, if I am on bypass, I still have battery backup. Isn't that correct? This is probably one of the most common misconceptions out there. You absolutely have no battery backup whatsoever if you are on bypass supply. Okay, whether you are in static bypass or maintenance bypass, it doesn't matter which one it is, you are not supplying the load from the inverter. So think about that for a moment. If you're on bypass, you're not supplying the load from the inverter. The inverter is the only component that converts the battery DC back to AC. So if the inverter is not supplying the load, you don't have any battery backup. Okay? So in this picture here, look at the red. Bypass supply is going through the transformer, through the static switch on the bypass supply, and out to the load circuits. You can see here I've put an X on the inverter static switch. That is off because the inverter is off. There is no way, look where the battery is. There is no way the battery can supply power through the inverter out through the static switch when you have transferred the system to bypass. It's impossible. So you do not have battery backup when you are in bypass. You are on raw grid supply. Whoever supplies power to your plant, you are relying on that power. Okay? Next misconception is the UPS says it's on bypass, but the switch is in normal. The bypass switch is in normal. What's going on? It usually means one of two things. Someone has pressed the bypass to load push button on the UPS, and that has transferred the system to static bypass electronically within the UPS. Or it could be that the system has automatically transferred to static bypass due to a fault. Now remember, the maintenance or manual bypass switch, which is a physical switch mounted either on the front of the UPS or external to the UPS if it's an RMBS, is not affected by the position of the static switch. It doesn't care. Okay, it's just a switch. So in this situation, the first thing that you should always try to do is press the inverter to load button on the UPS. And you have to understand, there's a lot of logic built into a UPS, and it is clever enough to know if there is still a fault inside the UPS present. So it will only go back to inverter if everything is okay. It will not jeopardize the load circuits. So if the system says it's on bypass, always the first thing you should do is try and press the inverter to load button. And if it doesn't switch over, you know there's something wrong. You have to go into the alarm log and figure out what's wrong. If it does go back to inverter, then the alarm will clear and everything is good. Okay, but you can see from this picture here, okay, the arrow is pointing to the static bypass switch. It's not the greatest drawing. I don't like the way it's drawn, but it is saying that that block there is the static switch, and the power flow is coming from the bypass source all the way through the RMBS contacts where the other arrows are, through the static switch and back out to the load circuits. So we are in static bypass at this point, but the RMBS is in the normal position. So that's the confusing thing for a lot of people, is the difference between the static switch and the remote manual bypass switch or the manual bypass switch. Okay, so the manual bypass switch in this situation is in normal, but the static switch is switched to bypass. So that's when you can go onto the UPS, press inverter to load, and see if it transfers back to inverter. Okay, at this point here, I would ask if there was any questions, but unfortunately, this portion of the presentation was recorded after the day of the presentation due to a technical issue that we had. What I would like to say is if anybody has any questions, please feel free to contact me. My email address is craig.williams@amatech.com. I hope you enjoyed this presentation. If you did, please let us know what you would like to see future presentations based on. We can go more granular on certain things on it. Say there was something within this presentation that you think I didn't clarify as much as you would like. Shoot me an email and I can look into that into a more granular way on our next webinar. We'd love to hear from you. We really, really do. We want to help you have faith in your UPS systems as much as we possibly can. We're here to help you. We're here to ensure that your critical loads are always being supplied. Obviously, you can follow us on LinkedIn. You're probably part of our mailing list as well, so look out for emails going out. Hopefully the next webinar will be within the next month. We're going to try and do this on a monthly basis. And obviously I have to apologize for the technical issues that we had initially on this webinar. We do apologize for that. It was out with our control, and I'm guessing we're not going to use Skype for Business next time we do this presentation, because that was the weak link and why we had the technical issue. So it's probably going to be a WebEx webinar next time. So once again, I appreciate your time. My name's Craig Williams. If you need to contact us, my email is craig.williams@amatech.com. And if you've enjoyed this presentation and you feel like you would like more training, you can get in touch with us. We have a fantastic training center here in Stafford, Texas. We have numerous UPSs that we can put faults on within our lab. It's a state-of-the-art lab. We have state-of-the-art classrooms, and we get nothing but fantastic reviews on our training classes on UPS and stationary batteries here at our Stafford training center. So once again, if you need any information regarding our training, just contact me and I will point you in the right direction. So I'm going to stop talking. Thank you once again. I really do appreciate your time. I hope you learned something during this webinar. And if you have any comments, please fill in the survey that we're going to send out to everybody. And if you want any direct questions answered, just email me at craig.williams@amatech.com. Until next time, thanks very much. Take care.